Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're going to go ahead and get started. Welcome to the MSR Colloquium. I'm very pleased to introduce Jason Hartline from Northwestern University. He was my colleague for several years, and he moved to Northwestern from Microsoft, so he's also been all of your colleagues at some point in the past. He's done a lot of phenomenal work on algorithmic mechanism design, especially focusing on approximations in mechanism design, and sort of spurred a whole field that looks at these kinds of questions. And today he's going to talk to us about mechanism design for data science. He's also very skilled at wearing purple.
Thank you. It's good to be back here. So this is joint work with my colleagues Shuchi Chawla and Dennis, who is also your colleague, who's frequently by here. And this has been, for me, a really fun collaboration between myself and Shuchi, who do approximation and mechanism design kind of work, and Dennis, who's an econometrician, trying to understand the interplay between mechanism design and issues relating to doing inference with data sets that come from economic systems. And so I am completely confident of Dennis's ability as an oracle for everything econometric. And so if you ever want to know something about that, you should definitely ask him. And any econometric mistakes that I make are because I misunderstood what he was telling me. Okay, so this is, when I think of what the promise of data science is, I think of the following high-level goal. The high-level goal is that, well, if we have lots of data from complicated systems where things are interacting, then if we can understand that data, we can use that understanding to then potentially make decisions or change the system so that things work better. Okay? So we might like to then, for instance, optimize performance with the understanding we have from the data. But frequently, if the decision we're making is then going to impact how behavior is then generated, then this decision we make when we optimize performance will then come back and affect the behavior in the system. What this means is we need to predict behavior in the new system to know if the changes are going to work well, not just know how people were behaving in the old system. Okay, so we're going to have to do something called inference, which is to see how people were behaving and infer how they're going to behave if we make any given change to the system. Okay, and a central observation that's going to motivate this work is that not all systems induce behavior that permit good inference. So it won't be the case that every decision you might make in optimizing performance will lead to a system where you can infer the things you want to infer so that you can then optimize the system. So because of this, we're going to need to understand how to make systems that are good both for inference and for performance, so that we can have this mentality of, oh, let's design a system and let's see how it's working and let's infer stuff from the data in that system and then tune the system in the future so that it continues to work well. Okay, today I'm going to focus on some problems in auction theory as my examples of where this situation is going to come up. But my perspective is that this kind of methodology applies to any system where the behavior is endogenous to preferences that aren't necessarily in the data themselves, but then have to be inferred from the data, and where behavior will depend on how the system is actually working itself. And so good. Okay, so I'm going to be motivating this work with simple auction examples, and I'll start out with a simple two-bidder, one-item, highest bid wins first price auction. Okay, so I have two bidders who want to win one item I'm selling, and I'm going to award this item to the bidder who bids the most, and I'm going to charge them their bid. Okay, and let's suppose this situation happens a number of times, and I have data sets for 200 different auctions, but from a similar population of bidders. Okay, so now the question is, suppose I care about optimizing my revenue. The question is, how should I adapt my auction to get more revenue using this data? Okay, well, to answer that question, the first thing I might want to know is what auctions get good revenue. And so if I turn to the economic theory, then I would learn, for instance, that the revenue-optimal auction for a large class of problems is just the first price auction with a reserve price, which is a nice, really simple auction. So instead of just running the first price auction as I did here, I'm going to run the first price auction with a reserve, meaning I won't accept bids below some minimal value. Okay, so that's the optimal auction. Good, so I have data. I know I want to run this optimal auction. I need to determine a good reserve price from my data. Okay, that's like the starting problem. Okay, so we're going to sort of walk through this example, looking at the data and what happens when we get reserves. I want to comment, though, that when I said I'm going to have data, what I mean is synthetic data that I made up from a model that I had in mind already, and not real data. Which is actually helpful for the stuff I want to do, because then I can tell you about every single counterfactual I might want to tell you about, because it's synthetic data. And this theorem requires some distributional assumptions, which I'm not going to tell you about, but it's not going to matter. Okay?
Are you at least assuming that the two bidders are symmetric?
Yes. Yeah, I'm assuming all of my bidders and all the auctions come from the same population, so they're symmetric. So was there another question?
And they're also independent.
Yes. Yes. Okay, so here's the data that I have. So we ran a bunch of first price two-bidder auctions, and I've numbered the auctions 1 through 200. I've shown you the two bids. I've shown you the revenue, which is obviously the maximum of the two numbers, because if I have two bids and it's first price, the winner is the bidder with the highest bid, and they pay their bid. So this is what's going on. So here's a first thing you might try to do to figure out how to come up with a good reserve price. And this is not going to work, but I just want to put this up as something that you might have thought to do before thinking about the endogenous behavior that's going on. So I could simulate the reserves using the old bid data. So I could assume that when I put a reserve, no one's going to change their behavior. They're just going to bid the way they were bidding before. Okay? And then I can just calculate what the new revenue would be. So, of course, when I add a reserve, I'm going to lose revenue because bids below the reserve are no longer, if both bids are below the reserve, then I get nothing, right? Because I'm losing revenue here. And with a reserve, bidders should raise their bids to account for the reserve, but because I'm just simulating with the old data, they're not doing that. So this would tend to drive bids back up, but it's not going to be happening here because I'm using the old data. Okay? And so the problem with doing this failed approach is that simulation does not account for bidders raising their bids at all. And as you might expect, as I simulate here using a reserve of 0.5, my revenue only goes down. Why? Because I'm just taking the places where they're both below the reserve and zeroing them out. Like here, they're both below the reserve, I just zero it out. So I just put zeros places where I was getting revenue. Of course, again, here because I have synthetic data, I can do the counterfactual and be like, what would really have happened had I used this reserve? Well, really, everyone would have bid more, and my real revenues are here, and I'm getting more revenue. Okay? And I could similarly add a higher reserve. Again, I'm zeroing out more columns here, getting even lower revenue. And with the real reserves, I'm getting even higher revenue. Okay, so the takeaway point here is that I really have to think about the model that the bidders have that's making them bid if I want to do anything. Because if I just simulate a new mechanism with the old data, it's not telling me anything useful at all. It's telling me the revenue is just going down, 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 when in fact it's going up, up, up. Okay, so I want to continue with this example and see what's going on with another perspective. So what I want to do is I want to take the bids that I've received in this auction and sort them by decreasing bid. So all the bids are here, they're all sorted, and I just normalize this axis to go from 0 to 1. So 1 is all of my bids, and 0 is none of my bids. And now I want to see what the behavioral revenue is if I actually calculate the counterfactual of what should happen versus my simulation revenue for various reserve prices I could post. And of course, if I have no reserve price, well, then that was where these things were the same. So they're both the same bids. And now I can think of adding a reserve price of 0.5. And in the simulation, what does that do? It just says everywhere you're getting less revenue than 0.5, you lop off the revenue. Right? And in the simulation, well, the people below are going to no longer show up, but now other people are going to bid more, and that's going to drive revenue up. Okay, and so to see how much, what the change was, well, we lost this little triangle here, but we gained all of this. Okay, so the revenue goes up. I use another reserve, 0.75. Again, we lose some, the revenue goes up again. And actually, as you can see, my bids are all below 1, right? Which if you had bids below 1, you're like, well, should I use a reserve price of 1? Well, that seems terrible if your bids are all below 1. But in fact, that's terrible for the simulation. But in behavioral revenue, that's actually still your revenues going up, right? And so somehow in my data, all the bids were below 1. And I'm saying, well, actually using a reserve price of 1 is great for this data. Okay? And in fact, now if I start even using a high reserve, the revenue starts to drop to 0.77 and then 0.65. And in fact, using a reserve of 1 was actually the best reserve to use in this situation. So is it clear what's going on? Okay, so that's my introduction. I now want to tell you what I'm going to be talking about in this talk. So I'm going to start talking about inference for predicting behavior in auctions so we can see what we have to do. So basically, we want to look at the data. We want to try to come up with the model that generated the data so then we can, when we change the auction, go forward and see what that new auction revenue would get. Okay, and then I'm going to look at revenue optimal auctions. So as I said in the first slide, the revenue optimal auction, for instance, might be a first price auction with reserve. And we'll see that this is not going to be a very good auction for inference. If we ran this auction would not have good inference. And so if we want to run a good auction to get good revenue, but also maintain the property that we can analyze our data and have good inference so we can tune the auction in the future, we're going to have to do something that's not revenue optimal. We're going to have to sacrifice revenue to get good inference. And so the last part of the talk will be to do revenue optimization subject to good inference, and we'll see the kind of auctions we get when we do this. Okay, so to start off, let's talk about how we're going to do inference, how we're going to infer what bidders would do in a different auction, given the auction we actually ran. Okay, and so the fundamental assumption for our auction is that the bidders are happy with the bids they made in the auction. Bidders bid, and before knowing what would happen, they're happy with the bid because they chose the bid, so they must be happy with it, right? And so more formally what this means is that bidders' bids must be a best response to the competing distribution of bids, right? If a bidder knew what the other bids were in the auction, they could then optimize their bid to figure out what the best bid was for them. Okay, and so they're happy if they've done this optimization. Okay, so what's nice about this statement, though, is that they're trying to optimize versus the competing bids, and the competing bids are what's in the data. We have a bunch of samples from the bid distribution, so we know what the bidders are optimizing against. So we can put ourselves in their perspective and say, well, for any value for the good you're selling the bidder might have, what should they bid in this auction, given that the competing bid distribution looks like this? And so given that, we can figure out what any value should have bid. And if we can figure out what every value should have bid, we can invert that function and figure out what values a bidder who bid something could have. And once we know their values, then we can get a distribution of values. And once we have a distribution of values, we can figure out what would happen in any other auction we might want to run. Yeah?
So you're assuming the bidders know the distribution of values that they're being drawn from?
No, I'm not. A bidder's bid must be best response to the competing bid distribution. I'm assuming that they have optimized their bid for the distribution of bids that are arising in the auction. So maybe they know the distribution of bids, or at least they've optimized to it, and changing their bid doesn't give them anything. Yeah?
But you are assuming that they know that the environment is stationary.
I am assuming that when they realize that changing their bid does not give them more revenue, they stop changing their bid.
So it's not it's not the same bidders, right? They can't infer themselves stuff.
The auctions I'm running are all different bidders every single time. So the story where someone learns is a separate story. I assume that each auction, there was a process of learning and then people bid that way. But I'm not talking about learning at all. They've somehow figured out how to do this. Okay, so good. Let's look at our example. This was the example data I had before. So our competing bid distribution is observed in the data. Great. Now we can figure out how someone might bid. So given the bid distribution, I want to solve for the bid strategy. Then I want to invert that bid strategy to get the bidder's value from their bid. So let's see this example for the data we have. Okay, so if I were to look at this bid distribution, I would say that looks really uniform to me. It looks like the line, if this axis I call Q, this is 1 minus Q. Okay, so it looks like a uniform distribution. Good. So if I told you you're bidding in an auction and the person you're bidding against is bidding according to the uniform distribution, how should you bid? And so suppose your value is V. Let's figure out what bid B you should make given that the competing bid is uniform. Okay, well, what is your utility given your value is V if you bid B? Well, if you win with your bid, then your utility is your value minus your bid. Because you gain your value, you pay your bid, that's your utility. Okay, good. And I know all these things because I know the probability you win with bid B because it's a uniform distribution. So for any bid B, I can say, what's the probability you win? Well, the other guy is random from the distribution, so they're either going to be here beating you or here losing to you. And what's that probability? Well, if it's uniform, that's exactly 1 minus B. Right? So that's this area. And so that's 1 minus B. And this is V minus B. Sorry. This is B, not 1 minus B. This little area, probably you win is 1 minus B. Probably you lose is B. Probably you win is B, probably you lose is 1 minus B. Good. And V minus B, so I've drawn this area, your utility, which is exactly this formula. Probably win with B is this width, and V minus B is that width. That's a rectangle. So what am I saying you're doing? You're trying to optimize the area of this rectangle somewhere here. Okay, and simplifying this formula, you get this equation, which you can take the derivative with respect to B and set it to 0 and solve. And you see that you should bid half your value in equilibrium. Like that's your best strategy. Good. Well, if I think that if you should bid half your value and I see your bid, then I know what your value is, right? Your value is twice your bid. And if the bids are uniform 0, 1, and everyone's value is twice their bid, then the values are uniform 0, 2. So now I know the value distribution. And so I did this for the uniform distribution. You can do this for any distribution. It's the same basic calculation. Okay? So, and then from value distribution, I can solve for the equilibrium behavior in any auction I want. And so now I can say, what's the optimal auction for this distribution? And I can tell you what it is. Okay, so we walk through this in pieces. If I put these pieces all together, then I would get this equation as a formula for my value as a function of the observables like the bid, and then when I differentiate, I get the derivative of the bid function, and this term, which is the allocation probability. So x of q is the probability the player who's the qth highest amongst the distribution of bids wins the auction, and x prime of q is the derivative of that function. Okay, and let's note this is the inference equation that we get out from doing that calculation we did in the previous slide. So what are these things? So this is the allocation as a function of how strong you are. That's known. And so for the examples I gave, this probability of winning is 1 minus how strong you are, and the derivative is minus 1. Okay, that's this. It's basically the function. The function we had before was the line 1 minus q. That's the function. And its derivative is minus 1. Okay? Now, our bids, that's what we don't know yet in the auction. We're trying to infer well, we can observe that in the data, but we don't necessarily know it. Without observing the data, we must infer these. Okay? And so from the picture we drew, we said, well, this distribution looks basically like 1 minus q again, and the derivative is like minus 1. And we plugged into this formula, and we inferred that the value distribution was like this, which actually the primes, they're both minus 1, so they cancel, and we get 1 minus q plus 1 minus q, which is 2 times 1 minus q, which is they're bidding twice their values. Yeah? That's just walking through everything we did before, but with an example. So good. So I want to basically imply this formula where the x's are known, and I have to get estimators for the bids and the derivative of the bids. That tends to be what you have to do this inference problem. Okay, so let's just see what are the issues with this. So if I have n samples from the bid distribution, then I can use standard estimators for b hat, and they have rate square root n. Okay, now it's going to be a little bit harder to estimate the derivative of the bid function, but there are standard estimators for estimating the derivative of the distribution you're observing, but they have rate that's bigger than square root n. And those are based on some assumptions like continuity, and basically the assumptions that you make then tell you how much bigger the rate is. That's also kind of standard. Where we're going with this, actually, is that we're going to be able to infer good auctions using only this and not this. So actually, if this part's confusing to you, then don't worry, we're not going to have to use it. But if you were to do like the naive, straightforward approach, you'd be using these two things and doing what we said before. Okay? One thing that you should note is probably pretty important. It better be that x prime of q is not going to 0, right? Because look, it appears in the denominator here. And if I'm trying to infer something and one of the things is going to 0, I could be in big trouble in the denominator, right? So that I could be worried about. That's going to come up probably on the next slide. Slide after the next slide. Okay, so that's the basic of inference. That's what you would do in auction, straight up applying econometrics to this auction problem. That's what you would do. Okay, now I want to talk about optimizing auction revenue and looking at whether they can get good inference from those auctions. Okay, so on my very second slide, I said the revenue optimal auction was the first price auction with reserve under some distributional assumptions. And I want to point out something super obvious. For bidders with values below the reserve, I cannot infer anything, right? Super obvious. But that came out of my formula also because the derivative of the allocation rule for those bidders is 0. So this thing I'm trying to invert, which has that in the denominator, is just going to blow up. Okay? So this is problematic. Why? Well, suppose I have a population of bidders, and we're using an optimal auction. We have a reserve price, and we're running this auction. And then we do some advertising, but our advertising only targets lower valued bidders. And so now more lower valued bidders show up, and it would be getting me more revenue to lower my reserve price. But I never see that in my data because I'm already using a reserve price that excludes these lower valued bidders. So this is problematic. So, and it's really sort of the motivating goal of this work is that optimal auctions don't necessarily give you good inference. So if you want to design good auctions, you're going to have to sacrifice optimality to get back your inference properties you want. Okay, good. So let's talk about revenue optimization subject to good inference. I want to change settings from a single item auction to a more general setting to talk about inference. And the setting I'm going to talk about is the one that people use to model the advertising on internet search engines. So Microsoft Bing shows ads on the side of the page. Those ads are shown in auctions. You typically model those with decreasing click probabilities for each slot. And that corresponds to this situation. So I have n agents or bidders. I have n positions. These are the slots on the side of the page. Each position has a probability of click, which I'll call weights, which are decreasing as you go down the page. Okay, I would like to design a good auction for this situation that has revenue and good inference properties. Why? Because I want to then look at the data and optimize my auction as the data changes. This has its special cases, the auction we were talking about before. So the single item auction is just this exact same thing, but where the weight for position 1 is 1 and the weight for all other positions is 0. And I can generalize that to give a multi-unit auction where the weights for the first, say, k of the positions is all 1, and the weights for all subsequent positions is 0. So most of my examples I'll actually give for this, and so we won't really be talking about this one. Yeah?
Question. So as the distribution drifts, will you be assuming that the bidders will actually be bidding according to the same distribution? Because, according to the new distribution, because the bidders don't observe the right bids.
So I'm going to assume that as the distribution shifts, the bidders follow the distribution. I'm assuming that the distribution is shifting more kind of slowly, and they'll be updating their best responses. And the distribution is observed by the bidders because as new bidders show up, they will be bidding for the strategies that they should bid when they show up, and so the bid distribution changes. Okay, so the point is, if I have all of a sudden more lower valued bidders, then I all of a sudden also have more lower valued bids. So I actually you do see this in the data right away.
I see. I guess the point is that the bids of the values below the reserve will not affect other people's best response anyway. So
we're not going to have auctions with reserves anyway, so that's not going to matter. Okay. That's the reason why is because we had no inference for these bids below the reserve at all in the first place. Okay. Yeah.
I have a question about your goal here. So maximizing revenue, we understand that technically, right? But when you say good inference, what do you mean? What does that mean technically?
So as an example of what you might need for good inference, a minimal thing is, remember x prime can't go to 0? So we need kind of a lower bound on x prime. How the allocation rule changes. So what is x prime? Remember, x is the probability of winning as a function of how strong you are. And x prime is how that changes as your strength changes. It's the derivative. Okay, and so if the auction is not very sensitive to how strong you are, right? It means like if you change your bid a little bit, nothing really changes. This is going to be really bad for inference for obvious reasons. Okay, so what's gonna turn out to we're gonna need for good inference is just a lower bound on x prime. It'll be that simple. Okay, so I want to give you an example of the kind of thing we're going to get, so that when I then say more formally what we're going to get, you'll know what the pieces correspond to. Okay, so let's imagine this n bidder k unit auction. So I have n bidders, I have k units. I can view this as a position auction, right, where the first k weights are 1 and the last n minus k weights are 0. Good. So here's a picture. My first k weights are 1. My last k weights are 0. So here's an auction you could run that would get close to the optimal revenue and have good inference properties. Let's let k prime be the expected number of units sold if we ran the optimal auction. So the optimal auction might use the reserve price, right? And in expectation, it's going to sell some number of units. Okay, it's not going to sell more than k units because it only has k units. It's going to sell k prime less than k units. So let's let k prime be about that. Okay, so here I've drawn k prime as some number less than k. Okay, again, viewed as a position auction, I now want to make sure that that people really want to be in the order that they're in. And one thing you'll notice here is that all these guys up here, they're kind of indifferent to where they are. They're all getting the good. And all these guys down here, kind of indifferent to where they are. They're getting the good. So what I'm going to do is I'm going to take mass and shift it downwards. Like this. So now everyone is really much happier in their position than in the next position. Okay, so I've added, it's like an epsilon stair where this width is epsilon. Okay, and adding this epsilon stair ensures that x prime is at least some epsilon, which will then come into my inference equation and let me show that I have good inference. Okay, so this is an example of what an auction could do to let you see like what the space of things looks like that we're going to be trying to do. And one of the things you can see here is we're basically simulating having a reserve price, but not really using a reserve price. We're actually just ordering the bidders, and if they're the k prime top ones basically win, but with slightly less probability as you are not less top, and the n minus k prime bidders basically lose, but they actually have a small probability of winning. Yeah.
I don't know if you're going here, but with neural nets, right, they had this problem that they could either have a learning mechanism or they could have things with step functions. And at some point, someone said, we could put a differentiable function that looks kind of like a step function in here by using a sigmoid function. Is that kind of where this...
Exactly. And one of the things that's nice about a k unit auction versus an auction with a reserve price, so the reserve price cuts off exactly at your value. So it's got a sharp drop at your value. Whereas a k unit auction, well, if we happen to have more high bidders now than average or less high bidders now than average, it actually smoothes out the step. Okay? So just a k unit auction is a really good auction. It's a nice smooth step. Just because if I draw random people from the distribution, I have potential of having slightly more higher ones than usual or slightly less higher ones than usual. So it gives you a very nice smooth function. And we're going to work directly with those nice smooth functions that we get out of the k unit auction. Okay? So a rank-based auction is an auction where I order the bidders based on their bids, and then how people get allocated depends only on this order and not on their actual bids. Okay? So in the previous slide, I'm assuming that I ordered the bidders by their bids, and then the first bidder got this slot, the second bidder got this slot, the third bidder got this slot, right, and got this blue probability. Okay? Now, if I actually had this constraint K, what that really means is I'm ordering them by the bidders and then running some auction that already throws out some, like sometimes doesn't serve the Kth highest person, right? And that's still a rank-based auction because that decision is made based on the person's rank and not based on their bid. Okay? So if I have a position auction environment with these weights, then when I'm optimizing rank-based auctions, what can I do? Well, I can take weight and shift it downwards. I can also take weight on low positions and just drop it. So dropping weight's like a reserve price, and shifting weight downwards is another option, another thing you can do. Okay, and again, here's my picture of what these two things look like. So I basically dropped this weight here, and then I shifted weight downward. Okay, so I'm going to be claiming that rank-based auctions have both good revenue and good inference properties, and so I'm now going to talk about how they have good revenue and how you optimize revenue, and how they have good inference and how you do inference for rank-based auctions. I'm going to do this at a pretty high level, though. Okay, so the first thing I want to do is consider running the k-unit auction for every k. If I have some auction situation, consider running the k-unit auction for every k and let pk be the revenue of the k-unit auction for each of the k's. And let's let w prime of k be the difference in successive position weights. So it's this, for instance, it was that epsilon that was going down, and then at k prime it dropped a lot. It was a big number, and then it was an epsilon going down in my picture before. So basically, you can view a position auction as a convex combination of these k-unit auctions. And so if your revenue for each k-unit auction is given by pk, and the convex combination actually has probability w prime k on being a k-unit auction, then you can just write your revenue based on linearity as this sum. Okay? What does this mean? This means a position auction revenue is given entirely and only by knowing what these pk's are. Okay? Which means if I want to do inference and I want to then optimize a position auction, the only thing I need to know for this inference is the pk's. I do not need to infer the value curve. Okay? So these are enough to do all the inference I want to do. Also, these are enough for the optimization I want to do, and so let's talk about this optimization. We need to know these P1 through Pn's to optimize, and the auction that optimizes revenue for these given P1 through Pn will actually look a lot like the optimal auction from the economics literature, except that optimal auction from the economics literature uses the distribution to determine revenues. And here we use this, basically we can view P1 through Pn as like an empirical distribution, and we're using those instead. So our optimal auction for these rank-based auctions looks exactly like the optimal auction in the literature, except that it uses the P's as the empirical distribution instead of the actual value distribution. Yeah?
So when you say the position auction is just a convex combination of these k-unit auctions, I'm assuming that you're randomized over k-unit auctions with k being randomized?
That's right.
And when do you announce this k?
You never, no, the point is a position auction is isomorphic to a situation where you pick the random k from a distribution ran a k-unit auction. And since they're the same, it's the same structurally, that means people play the same way in them, and it means the revenue is the same in the both settings. So I'm actually going to run the position auction. I'm not going to pick a k and then run a k-unit auction. But the revenue I get is the exact same in the two situations. So if I want to talk about the revenue, it's the viewpoint of randomizing over k and picking k with this probability is a good viewpoint for understanding how to get revenue.
What confuses me is that I see that point of view for incentive-compatible auctions, for non-incentive-compatible auctions, is it clear that the people will play the equilibrium just as a
Revenue equivalence.
okay? Okay, I see.
Yeah.
For those of us who are not versed in auction theory, like what you were optimizing in the very first example you were doing before, you were having this idea that there's going to be reserve price.
Exactly. And so when I say they're structurally similar, what do I mean? The optimal auction that's rank-based will have a reserve rank. Okay? And everyone above the reserve rank wins, everybody below the reserve rank loses. Okay? That's exactly what I mean. So any sort of intuition that you have from optimal auction theory will translate directly to let you think about these things. So if we had the intuition it was a reserve price auction, then that intuition translates exactly to a reserve rank auction.
And just so I completely understand where you're going with this, the problem before with the reserve price auction was you could have real data that you'd gotten from some people, but because of this property that you can't tell what the people who fall below the reserve would have done, you can't figure out a way to use your existing data to come up with an optimal reserve value. And with this approach, you can now, in theory, run it on some people and then later on decide what a reserve value should have been based on them.
Yes, and because of the point you made earlier, the reserve rank auction has a smooth allocation rule because of this people coming from a distribution, right? So it looks more like this the sigmoid that you were talking about, whereas the reserve price auction drops abruptly when your value gets below the reserve. It goes to 0 there, right? And so it's got this abrupt thing, which means you can't do inference below. But I'm actually going to make an additional change, additional fix that I can also add this constraint that I want the changes in successive positions to be at least epsilon, which is in my previous picture why I got these steps going down. Okay, so if I don't do this, I will still have not so good inference at the far away from where it drops, right? And this makes sure I have good inference everywhere. So this is just optimizing rank-based. If I want to optimize subject to good inference, I add this constraint. Yeah?
The one item auction, it's clear to me what assumptions you need to make to get unique equilibrium. The Edelman structure.
So for a one item auction, the Bayes-Nash equilibrium is unique when the players are symmetric.
Right, but here in the multi-object item,
For position auctions, it's also unique.
it's unique. But is that an assumption that you need to get?
Excuse me?
Do you need this to get identification? Because otherwise you can assume that it's there.
No, you don't need uniqueness of equilibrium to get identification. Because people are just best responding to the bid distribution, and you're observing the bid distribution, and so you can see what their values are.
Yeah, but it's not clear that maybe like some periods I'm looking at one equilibrium, and other periods I'm looking at a different equilibrium.
That's true. You would have to be, so for instance, if I wanted to look at potentially other equilibrium, I mean, the equilibriums are unique, so talking about this is kind of like an academic exercise. If you had a situation where the equilibrium were not unique, and I sort of said, okay, there's player 1 and there's player 2, and each time I assume that player 1 and player 2 are playing in the same equilibrium, the same not unique equilibrium, then I can do the same thing. Right? Obviously, if people are picking higgly-piggly each time which equilibrium they're playing, I don't know what I could say. Okay, let's talk about inference for these rank-based auctions. So as I said before, the allocation rule is known because it's a rank-based auction, and we've written down what the position weights are, and essentially we're then looking at how this gets smoothed out by drawing from a distribution, which is, again, like the sigmoid, right, which smooths it out a little bit, but we know exactly how it's getting smoothed out. We need to estimate these P1 through Pn. And you're able to estimate P1 through Pn based only on the bid distribution, which you see in the data, and x. You do not need the derivative to estimate these p's. I'm not going to go into details about why this is the case. The intuition is that it comes from this, actually the smoothness of the allocation rule. Okay, and therefore our estimator has this ideal rate of root n, which is the best rate you can have for an estimator. Okay. So I want to summarize with sort of, if I were to write a theorem statement with what is the main result here. The main result here is if you give me any position weights and any value distribution, then I can come up with a rank-based auction which approximately optimal in terms of revenue and has good inference properties. And the way I do it is like on the previous slide. I used basically optimal auction theory, but applied to the empirical distribution given by the P1 through Pn's. And I get good inference by maintaining that the successive slots have at least this epsilon drop. I'm going to have made some very mild assumptions on the distribution to get this theorem. I can't have really, really heavy-tailed distributions, meaning a bidder shows up only once every sort of million tries who has a really high value. Like that I can't deal with. But for things where that doesn't happen, then you're fine. Okay, so to conclude, system performance and inference depend on the design of the system. So if you're thinking about optimizing a system and you want to be able to re-optimize your system as you get data for your system, and your data is based on people's behaviors, but not based on their actual, based on their behaviors, and you don't observe their actual preferences, then you need to think about designing the system itself to have both good inference and get good performance. We talked about how the optimal auctions, which are value-based, by using reserve prices in value space, are bad for inference. We saw that rank-based auctions are good for inference, and we can get approximately optimal revenue with those. And we saw that structurally, these optimal rank-based auctions look very similar to optimal value-based auctions. They just use ranks instead of values. And here is my picture for kind of what it looks like. Thank you. Yeah.
I guess this would bring up the question. You mentioned this epsilon that you need to figure out how good for your inference. And this epsilon also must have some relation to how much you're losing in optimality.
Yes.
And
that's great. So here's the point. The way to think about this is, how many samples do you think you're going to have before the world has changed enough that you want to change your auction? Okay. Look at that many samples. Now choose an epsilon so that you've inferred enough with that many samples, and that's the right epsilon. Obviously, the smaller epsilon, the better. So you choose the smallest epsilon where you've learned enough in that many samples to get what you want to know. Does that make sense?
I guess this next question will probably move beyond where you guys are because you're theory people. Do you have any ideas of places or auctions or things that you might do where you can take a look at and figure out what that epsilon number might be for something real worldy, like I want to put my clarinet for sale on eBay with a reserve price of X? Could I use this to study the previous clarinet sales of similar people to figure out anything fun?
So this is naturally set up for this situation of position auctions, which are how people sell ads on search engines. And so that's one example where you could think to try to do this instead of what people are doing, which is using reserve prices. Okay, so one thing I will say is that we've been looking at this in the sort of big N, big K case because we want to understand situations where it could be really hard to get good revenue. If I have small n and small k, actually lots of things get good revenue, and I can't really separate good from bad very easily to understand structurally what's good and what's bad. In a real situation you're probably thinking of running, you probably have small k and small n. Like so for the position auctions, maybe I have 30 advertisers, and maybe k is like 6 ads on the side of the page. And in these cases, when k is really small, you don't even have to do the thing with the epsilon. Okay, because what you care about is the derivative of the allocation rule, and for that few number of bidders, these things that are smooth are already going to put smoothness everywhere. Okay, so you actually wouldn't even do a thing with an epsilon. You just do a rank-based reserve, essentially. Yeah.
So you're assuming that advertisers are going to respond to the fact that you might use their bids to change future reserves? Or is the idea that it's different advertisers, so it wouldn't?
So the model I'm talking about here is just a pure inference model where I assume the bidders are new bidders each time. So there's no strategic behavior between the people I'm observing and the prices I'm changing in the future. None at all. And I'll tell you, getting to that, so there's been a lot of work on how to do inference, how to learn the distribution on the fly when mechanisms have truth-telling equilibrium, when everyone says their value, right? And here the inference problem is trivial because everyone says what their value is, right? And so this question, though, gets at what happens when people don't want to tell you their value because you might use it against them in the future. And so combining these two areas, you would get a theory for how to do inference and deal with people who are worried about affecting their own prices in the future. Right, so that would be like a logical next step is to merge these two theories and write that paper. Yeah.
Maybe like when you think about Facebook or something like that, it's a more natural environment because in AdWords or stuff like that, it's a repeated game, right?
Absolutely, I agree. So this issue of the same bidders coming back would be a problem.
But with Facebook, you would normally compete against a different set of at least.
Yeah, perhaps I'll do this inference looking across many different keywords instead of successive draws of the same auction.
But then you're not taking, it's not the same environment.
Yeah, but if so, for instance, you might group keywords based on they have similar distributions, and then and do something like that, which is actually, I mean, there's a paper that looks at estimating reserves for ad auctions, and that's what they did. Yeah.
I have a question not so much about the value per base versus rank base, but as somebody who doesn't know auction theory at all, it seems that whenever I encounter these kinds of discussions, that it's always about raising revenue for the person who's doing the selling, which makes sense if you're Microsoft and you've got Bing, for example. Can this be flipped around? Is there some way to turn this on its head, or is it a completely different set of questions to ask? How do you save the most money and get the most stuff cheapest? Because that seems like a huge auction game theory algorithm problem also. Is that just a totally different, or does this
no, so
turn it upside down or put a mirror in front of it? Or
so I like to use revenue as an example of an objective that the designer might want to optimize. I like to use it over using something like social welfare, which is another example of an objective. And the reason why is because optimizing social welfare in auctions doesn't require any distributional knowledge at all. Whereas optimizing revenue does require distributional knowledge. You have to tune the mechanism to the setting you're in. And in general, most objectives do require having distributional knowledge. So revenue is an example of one of the objectives that requires distributional knowledge. And welfare is not, okay? But for instance, if you were trying to, suppose you were trying to optimize the utility of the players and you don't care about the payments made to the designer. Like maybe you're the government that doesn't care about its own revenues but cares only about the utility of the players. In this situation, this is not welfare. Welfare is the welfare of everybody, including the designer and the players. So if I just look at the welfare of the players, right, the exact same theory that I put forth here can give you optimal auctions for this objective of the utility of the players. And it will look exactly like this. Yeah.
Could this approach be applied to something like voting, in which a government or some sort of entity is trying to, as you said, maximize social welfare, and people who are voting aren't truth-telling, so you're trying to infer their true preferences?
So
Truth-telling and voting.
Perhaps there's an incentive to not.
Party. Sometimes you prefer the third candidate, but he's
Oh,
not going
to
to
screw
win.
you up.
Yeah.
So the short answer is the challenge. So the short answer is yes. The reason why you could look at social welfare with voting is because you don't typically allow transfers in voting, like there are no payments. And that makes it not like the standard welfare situation in mechanism design where you allow transfers and then things become easy. So you can look at these kinds of questions for voting. The difference between the class of work that this falls in sort of optimal auction theory versus voting theory is that voting theory tends to not be using a distribution. But if you were to try to do voting theory with distributions and come up with a voting mechanism that was good for your distribution, then you could try to get a theory like this to work. And you would need to get a theory like this to work, to make that work. I don't know of much work in that area myself. But it's a great area to explore, for sure. Yeah?
So this solution is not the unique way to do this that optimizes your revenue and has good inference properties, or approximately optimizes revenue and has good inference properties, right? And so what I assume Microsoft is doing, and Google and all these things, although I don't really know, is like they have a rank-based top K, people get the top K slots, but then they do some preferential randomness, like occasionally allocate. I mean, maybe Rob can.
It would be smart if they did something like that, but there's a lot of randomness in the system, so the curves are kind of smooth. So we're kind of relying on that giving us what we need, but it's probably not optimal.
So this brings up a good point, which is you could imagine having other auction rules which guaranteed the smoothness, which means you could do good inference. I want to point out that rank-based rules have another nice property over rules based on values, which is that rules based on values, the actual allocation rule X is then also endogenous to how the values map the bids. Okay, whereas a rank-based rule, your probability of winning is a function of how strong you are. Does not depend on your value at all. It just depends on what order you guys are in. And in these rank-based auctions, everyone lines up in order of value the same way. So the allocation rules are just known. Okay, as an example, so I said the optimal auction has a reserve price under many distributional situations. Under some of the more extreme distributional situations, you have a reserve price, but also some interval where you basically treat all bidders the same. Any bidder who bids in this interval, you treat the exact same way. And if that interval is now in bid space, so I say no bids below $5, but bids between $10 and $20, I'm not going to sort you in order. I'll put you in a random order. Okay? Then where does 10 to 20 in bid space fall in value space? Well, that depends on the equilibrium. Okay? So now I don't know what the allocation rule was. And so this makes it much harder to do the inference properly. And so that's going to be a big challenge in trying to do inference with non-rank-based auction rules.
But I could stick to rank-based and do some other allocation function.
You could stick to rank-based and do some other allocation function. So if your goal is to optimize this subject to this, this is the optimal. You can just write that optimization problem and do it optimally. A point you could be making is the actual thing you need for good inference is not exactly this. This guarantees it, but it's not exactly this. You can actually write down what the function is and then do it exactly. Okay, and I haven't bothered to write it down here for you. It's complicated. And analytically solving for it is actually also not so easy, but if you have a computer doing this thing, you just have the computer do it. Yeah?
How does this compare online learning. So the very first example where I have all these different prices I might try, I'll just try them in embedded online learning.
Yeah, that's a great question. So one of the things that I like, one of the things I really like about this approach over the online learning approach is if I'm imagining my population of bidders distribution is changing slowly over time, and I'm evolving with that with one mechanism that I run, and everyone knows this one mechanism I'm running, and it's changing a little bit, and the bids are changing a little bit, and they're just adapting.
So even the population of valuations change over time, not just the way they react to your mechanism? That's what you're saying? Or?
Okay, so the premise of doing inference in a system is that I want to know if, suppose I knew the distribution starting out and I optimized for the distribution and I ran this mechanism, right? Now, why would I want to do inference? Well, I want to see if maybe things have changed. Maybe I've done advertising and got some more bidders, and I need to adapt the system to still perform well for this change. Yeah. So if you imagine you're in a situation where the distributions are gradually changing, and you're gradually adapting the mechanism because you're doing inference to adapt to this changing system, then everything changes a very little bit at every step. Okay? Now, I want to compare this to the online learning approach. So an online learning approach says, well, there's a large space of mechanisms we can run. So let's pick different mechanisms from this space to make sure that we learn which one is good and run a different one each time. Okay, and the problem I have with that approach is that changes the mechanism completely every single day. And I need bidders to be in equilibrium for this mechanism to even work at all. So it doesn't make any sense for me. So the equilibrium assumption, the assumption that players are best responding to the mechanism, that requires them to have known that this was the mechanism. And if you're changing it every day, how are they going to best respond to the mechanism?
Yeah, this was sort of related to my second question.
So the problem is this is exactly the point, right? If you don't have a somewhat stable mechanism, bidders won't be able to figure out how to bid in that mechanism, and it's going to be probably mayhem.
But you can only try incentive compatible ones, so everyone doesn't.
Actually, I'm not using any incentive compatible mechanism here.
But I'm saying
And
in the online learning.
Let me tell you why I don't want to use incentive compatible mechanisms. Okay. So in real life, no mechanism is incentive compatible. Okay, in real life, these learning mechanisms are not incentive compatible because the guy who was bidding in Bing could bid on Google instead. Okay, so saying his true value in Bing is not a good strategy. Okay, so in real life, you never have incentive compatible mechanisms. Given you never have incentive compatible mechanisms, we need to do inference. Now, if you have a mechanism where you're changing non-trivially what the mechanism is doing every stage, then the statement that we are in equilibrium is probably a bad assumption. Right? Equilibrium is saying we're trying to be in steady state, and if you're changing it every day, you're not in steady state.
I mean, that point seems problematic for pretty much all of auction theory. That there are other auctions out there that like Google and.
It's especially problematic for truthful auctions, actually.
Why is it? Okay, so that's certainly
true. There's a fantastic essay by Ausubel and Milgram called "The Lovely but Lonely Vickery Auction,"
right.
Which basically talks about this second price auction, which has truthful bidding as a dominant strategy, and says why you never see this in practice.
Yeah, right.
And one of the reasons why is because it's really not robust to out-of-model phenomena like other things happening, whereas other auctions are much more robust.
What's the way one quantifies that?
What's the way you quantify non-robustness to out-of-model phenomena?
You talk. I mean, it's just a qualitative thing. I mean, I'm not familiar with this area, but.
So, for instance, I have some work quantifying this using approximation, which says that if the mechanism is good with approximately good without modeling this phenomenon, it's still good, right? Where if it's not, if it destroys everything when you add this out-of-model phenomena, then it's not still good. So that's one way you could try to do it. In this paper, they don't take that approach. It's a more this is less grounded in theory and more sort of observation, like this is what we observed and this is why we think that these are not working. These are some bad properties, and they sort of try to map on what's happening in the auctions to, so, yeah.
Given the single auction that you would build in this inference, do you think, are you positive that you can have situation that you can hold truthfulness instead? With just single auction, but you have inference. So
I'm not sure about your question.
we have
What about truthfulness?
We have truthfulness for like some auctions, but now you are building this inference on top of it. On top of
So
the
if I have a truthful auction, I don't need inference.
Yes, yes. I'm saying
So why am I building inference on top of a truthful auction?
No, not on top of truthful auction. I'm saying, can you imagine just one auction which has inference on top of it, which would be also truthful? Can you imagine like proving truthfulness for such auctions?
Again, I don't understand the question, because if I have a truthful auction, I don't need inference. So why would I build inference on top of a truthful auction?
If the valuations change over time, why won't you need inference?
Because I have a truthful auction.
The valuation, you need to somehow learn how the valuations change, right? So
But it's a truthful auction, so I do see the valuations.
Yeah. It seems like very simple inference, but you need the inference. You need to guess how the valuations change.
The point is it's trivial inference, and therefore you have not much to do. And you can look at all of the literature that looks at doing, basically learning the distribution on the fly. So the literature on prior free auctions, which does this.
I think we should take the rest of the questions. Thank you.